Okay, in section 5.5, here we want to look at one additional type of factoring called difference of squares. Okay, the process of solving the quadratic will be the same. You're going to set it equal to 0, factor, use the zero product property, and then solve for the variable. Okay, so a difference of the squares will only have two terms. It'll have two terms. It'll also have both terms being perfect squares. Well, what's a perfect square? Well, a perfect square, if we look at our multiplication tables, is any time you have a number times itself. That would be these. 1, 4, 9, 16, 25, 36, 49, 64, 81, and so forth. Those are your perfect squares. So a difference of squares must have perfect squares for both the first and the last term. And here, x squared is a perfect square because x times x is x squared. It's a number times itself. Okay. And the last requirement for it to be a difference of squares is the second term must be subtracted from the first. So the sign in between these has to be subtraction. If you have that, you have a difference of squares. Now, how do you factor a difference of squares? Well, factoring a difference of squares actually just happens to be the answer ends up being conjugates. So let's look at, let's write that out, conjugates. Okay, refreshing our memory on conjugates, if we had 2 plus the square root of 3, what would the conjugate be? It would be 2 minus square root of 3. If we had 3 minus I, the conjugate would be 3 plus I. Well, difference of squares factors into conjugates. They're conjugates. So what you do is you take the square root of each term, and these are the first and last terms of each factor. So you take the square root of x squared, well, that's the first term in each. Because the first term in each has to be the same. See how in conjugates, their first terms were the same? Then you take the square root of the last term, which is 9. And that's going to be your last term. Because see, remember how the last terms were the same? Well, the last term stays the same. And then you're going to make one factor addition, the other one subtraction. So one adding, one subtraction. Because see how those were opposites? Okay, so now that's equal to 0. Now, the reason why this works is first term times the first term gets you the first term. Last term times the last term gets you the last term. But notice how there was only two terms. There wasn't a middle term here. There wasn't a regular x term. Well, what happened to that? Well, remember on conjugates, the outers and the inners cancel. So there is no middle term. This is negative 3x, this is positive 3x. They cancel, which is why we have no middle term. So now, you've got x plus 3 equals 0, so x equals negative 3, and x minus 3 equals 0, so x equals positive 3. Okay? And you might even recall that we actually solved this problem back in Unit 2, and we solved it by just bringing the 9 over, and then taking the square root of both sides, and recall that a lot of people put 3 as the answer, and I marked off. Because there's supposed to be two cases, a positive and a negative. Because if you square a positive, you get a positive. Square a negative, you get a positive. Well, now that should be pretty obvious that there's a negative and a positive because look at your factors. They're opposites. Okay? So, doing one more example, we have two terms. Good chance that that's a difference of squares. So 9x squared, that's a perfect square. 1's a perfect square, and we've got subtraction. So, write out our two sets of parentheses. First term in each would be the square root of 9x squared, which is 3x. Last term in each would be the square root of 1, which is 1. Make one positive, one negative. So now you've got it factored. So you got 3x plus 1 equals 0. So 3x equals negative 1. X equals negative 1/3. That's your one answer. And then 3x minus 1 equals 0, so 3x equals 1, so x equals positive 1/3. And there's your two answers. Okay? So that's difference of squares.